a century, so I became aware that many physicists did not understand the physical meaning of this physical quantity called action. Sometimes also among this defended already his PhD thesis, when I asked him, can you explain what does it mean, this physical quantity action? They was astonished. But do you know the principle of least action? We have heard something. So you see that this quantity is not so well known among physicists. Let's begin with the explanation of the physical meaning of the used in physics quantity called action. The action in the nature manifests itself as the transfer of momentum along certain path. So we have the product of momentum and the path, this is action, and as the transfer of energy during certain time interval. In the rotational motion, action manifests itself in the transfer of angular momentum when the angle of rotation increases. Always we have a product of these two quantities. In the accelerated motion, in classical physics, the action is expressed as the product of the acting force and the path and time interval of its acting. You see it is a product of the force, the path of length and time. Since F multiplied by the path is the work, and F multiplied by delta T is the impulse of the force, we can obtain also action multiplying the work with the time interval and the impulse of force with the path. The non-Polish physicist Czesław Białowski has often pointed out that action is the richest in meaning physical quantity because the notion of action expresses a physical dynamical process in which dynamical quantities are connected with space-time quantities. Both of them play their part in the physical processes of action in the nature. Here we have on the one side the dynamical quantities, on the other side the space-time quantities, and you see that always the product of momentum, path, energy, time, angular momentum, angle of translation, force, path, time. Always on the one side hand we have the dynamical quantities, on the other hand the space-time quantities. How to get The physical quantity called action has been introduced into physics by Pierre-Louis Moreau de Maupertuis. Maupertuis formulated also the least action principle. The principle of the least action states that the trajectory of the transfer of momentum and energy between 2 points in the space and time is always the least. However, when the variational calculus has been introduced into the examination of the mentioned principle, it has been discovered that action is submitted to a larger variational principle because it is not only a minimum, but in certain cases it can be also a maximum. The trajectory of the transfer of momentum and energy is then the greatest. Therefore, it is now more correct to call the principle of extremal action. It is often called also principle of stationary action. The principle was central in the classical physics and remains central in modern physics, being applied in the theory of relativity, in quantum mechanics and quantum field theory. In general relativity, applied to the cosmos, it is with the Einstein cosmological constant, lambda, the Lagrangian of action has been the following form. Now some pieces of information on the so-called natural units determined by universal constants and parameters. As it well known, at the turn of 19th and 20th century, Max Planck has not only introduced his very important constant, called by himself the elementary quantum of action, but he has also at the same time introduced his natural units determined by three universal constants. C, the velocity of light, G, Newton's gravitational constant, and his constant H, the elementary quantum of action. The scientific community has soon recognized the importance of Planck's constant that became the quantization parameter of the newborn quantum mechanics. As regards Planck's units, the scientific community has long time ignored them. So Planck, during 12 years, has added to all his papers his units, believing that the community will finally recognize also the importance of his units. Later, especially the cosmologists have recognized their importance, and nowadays in cosmology we speak even about the Planck's era, existing at the beginning of the cosmic evolution. Something similar happened earlier when in 1874 the Irish physicist George Stoney, who is famous for his introduction of the term electron to describe the elementary unit of electricity, and for his calculation of its value from Faraday's law of electrolysis, introduced his physical units of nature, determined by the velocity of light, Newton's constant, and the elementary unit of electric charge. The scientific community has recognized his discovery of electron, the existence of which was proved experimentally in 1897 by Thomson, but Stoney personally was convinced that the discovery of his natural units is more important, and therefore he published his paper with the title Physical Units of Nature. You can find it in the Philosophical Magazine. Stoney and Planck believed that their natural units of physical quantities are more important than the used in mechanics conventional units CGS and now SI. Their belief was based on the fact that their units are not conventional but natural because they are determined by universal constants. However, note that there are as many sets of so-called natural units as there are charges of interactions, because they are determined not only by C and G, but also by the respective charges. Thanks to Planck and Einstein and other known physicists, we know that in the micro world, action is quantized. Such quanta of action are constant and can be interpreted as elementary, indivisible physical events. The transfer of energy, momentum and angular momentum is a physical event that happens along certain path during certain time with the increase of the angle of rotation. So a quantum of action has the nature of an indivisible, elementary physical event. And therefore, in the micro world, we are dealing with the real, indivisible, elementary atoms of action. For example, Eddington called the Planck's and the Stoney's indivisible portions of action atoms of action in his book New Pathways in Science. The quanta of action, Planck's and Stoney's, are the basic sources of other quantizations. Planck's quantum is the source of energy quantization, of momentum quantization. Here, 2p you have to put. And angular momentum quantization, like emission, absorption, and scattering of real photons. These phenomena are examples in which we are dealing with the elementary Planck's H event. Stoney's quantum of action, the source is a source of energy. What we have here, the Stoney quantum of action and momentum. Quantization in virtual phenomena. For instance, in the interaction between two elementary electrical charges in which we are dealing with an exchange of virtual photons. These phenomena are examples of elementary Stoney's events. Planck's and Stoney's quanta of action are very small. In the SI system of units, Planck's constant is given by the following numerical value. There are also other very small quanta of action connected with the four fundamental interactions. For instance, the mentioned already quantum connected with the electromagnetic interactions called Stoney's quantum in CGS, and here this value in the SI system of units, where E is the elementary electrical charge and K long constant. Are there also mega quanta of action connected with lambda interaction? No answer. To answer this question, let's first introduce lambda units. Lambda units and lambda mega quantum of action. Let's first introduce lambda units using the three Einstein's general relativity constants. C, velocity of light, K, the Einstein gravitational constant, and lambda. The lambda mega quantum of action is among these units. Since the exact numerical value of the cosmological constants lambda is not yet known, we shall use its approximative value. Then you see the lambda length is equal to 10 raised to the 25 power of meter, lambda time 10 to 70 second, lambda mass, lambda energy. Let's add the lambda action. Lambda quantum of action is equal, as you can see, the inverse of the three Einstein's constants: velocity of light, K, the Einstein gravitational constants, and lambda, the lambda constant, the cosmological constant. From the aesthetical point of view, it's very nice now. The inverse of three Einstein's constants.
Excuse me, you have 10 minutes. 10.
10 minutes. Okay. Several lambda units are used since long time in general relativity and cosmology. For instance, lambda density is known from the Friedmann equation. Here are other examples. Let's begin with the so-called pressure of the physical vacuum, or lambda density of energy. Is used in the quoted in this paper, action Lagrangian is present the lambda force at the first place. We're dealing with the very great lambda force placed at the first place. Note that we can, the quoted above Lagrangian, transform in such a way that the lambda mega quantum appears explicitly and is placed at the first place. In such a way, we can see how the action in general relativity with lambda depends in a natural way on the lambda mega quantum of action. In quantum mechanics, we use the notion of Planck's charge. If we introduce in similar way the notion of lambda charge, then the action Lagrangian can be written as follows, or also with the sign of this charge. In such a way, another aspect of the physical process called action, thus the dependence on is shown in the Lagrangian. Note that the lambda length and time are of the same range as Hubble length and time as regards length 10 to 5 meter, as regards time 10 to 70 seconds. Let's try to interpret the mega lambda action as a lambda mega event that happens in every Hubble sphere. In a Hubble sphere, because of the lambda force that causes the lambda pressure, the sphere expands with the lambda acceleration, and the dark energy performs a work equal to the lambda energy during the lambda time. The resulting momentum along the lambda radius equal to lambda length gives the lambda action. Since action consists in the transfer of energy and momentum during a certain time and along a certain path, therefore the product of lambda energy at lambda time and the product of lambda momentum and lambda length gives the lambda action. That is performed during the lambda time and along the lambda radius. So in the Hubble sphere, we are dealing with a mega lambda action event as the work done by the dark energy during the age of our universe. However, is such an interpretation well done, or it's simply false? We have to enter in details. According to several authors, especially those who formulate the great inflation theory, the so-called cosmology constants lambda is time-dependent. Then all lambda units are time-dependent because they depend on lambda. Multiplying the lambda mass with lambda acceleration, we receive the lambda force. By doing so, we are dealing with a Newtonian force. Can the Newtonian force play a part in the relativistic cosmology? However, the lambda force is used in the relativistic cosmology in its Lagrangian action. Does this create difficulty? How to interpret the lambda acceleration? We know that the acceleration of the universe expansion is not constant. It increases. But lambda is time-dependent. Then the lambda acceleration is also time-dependent. The whole list of lambda units expressed using Cg and lambda, and also with Ck and lambda, can be found in the appendix of my paper that I will give to publication. In the paper you will find also the discussion of interpretation difficulties with more details. I shall do more details analysis in my paper that I am going to present for publication. There is another mega quanta of action connected with the Kittle's units of Hubble spheres and Kittle mega quantum of action. In a Hubble sphere, we are dealing not only with dark energy, lambda energy, that causes its expansion, but also with gravitational energy that causes the gravitational attraction. Therefore, we have to look also for the mega-gravitational units which concern the Hubble spheres as the zones that are causally bounded also by gravitation. Kittel has indicated gravitational units for every concrete mass. We have here these units. If we introduce in Kittel's units the approximative gravitational mass of ordinary matter plus dark matter, gravitationally bounded and embedded in Hubble sphere, then we can introduce a gravitational mega quantum of action. Note that the gravitational Kittel length and time are given then by these values. Once again, we see that these values are equal to the age of our universe. An interpretation of the mega gravitational action as a gravitational mega event that happens in a Hubble sphere. Note that also the gravitational length and time Kittels are of the same range as Hubble length and time. As regards length, 10 to 25 meter, and as regards time, 10 to 70 seconds. Since action consists in the transfer of energy and momentum during a certain time and along a certain path, therefore, the product of gravitational energy and gravitational time and the product of gravitational momentum and gravitational length give the gravitational mega action that is performed during the gravitational Kittel time and along the gravitational Kittel radius. So in the Hubble sphere, we are dealing with a mega gravitational action event. It is as the work done by the gravitational matter, normal matter and dark matter, during the age of our universe. However, is such an interpretation well done, or it is simply false? We have to enter into details. I shall do it in my paper that I am going to present at the publication. Note that in the both cases, we are dealing with the similar path and time interval of both actions, but the lambda energy is greater than the gravitational one. Therefore, the lambda action is greater than the gravitational one. Therefore, the universe is expanding. Therefore, lambda action can no more than the conclusions. In the macro world, the gravitation and lambda interactions are very weak and therefore totally negligible, except for instance the gravitational interaction between two neutrons. However, both interactions have to be taken into account in the mega scale in which they are very strong and can in no way be neglected. Are they really two time-dependent mega events performed, one by lambda action and the second by gravitational action? If yes, then Hubble spheres causally bounded by gravitation and lambda interactions are results of the two mega actions. As the beautiful form of the from the aesthetical point of view, lambda quanta of action, to say anything in the relativistic cosmology or nothing. Can it really be interpreted as mega events? Is our universe composed of tiny elementary constant events and of time-dependent mega events? Thanks for your
Questions?
I have a remark on Planck's units. When Planck has defined his units, you understand, yeah? Okay, but at that time it was assumed that gravity was the most simple, most fundamental, and best understood force in the world. This situation has severely changed. At present, gravity is very badly understood, to say it this way. We are not even sure whether the gravitational constant, which is difficult to measure, whether this is a constant over the time. So this gravitational constant is a part of Planck's units, shows that Planck units are not defined in a good way. And my recommendation would be not to use them any longer. Perhaps they could be redefined by other basic units. Then it would make sense again.
Yes, there are many authors that consider gravitational constants as time-dependent.
We do not know what it is. We do not even know whether gravity is a force. Maybe Einstein says it is a geometrical appearance, something like that. Or it may be a side effect of another force. It's least understood. The former president of the German Einstein Institute, whose main topic of research was gravity, has said it's his statement that gravity is one of the least understood or the least understood phenomenon in our present physics. And to take this as a basic unit, this gravitational constant as a basic unit, it was a good idea by the understanding of Planck, but this is now outdated. It's no more a good definition.
I found out the postcard in the library of the Jagiellonian University in Krakow, and Einstein, that was a postcard of Einstein. He sent his general relativity paper to Polish physicist Natanson, and he writes, you will see how I have reconstructed my house of cards. The house of cards by Newton lasted 300 years. Mine will not stay so long. So you see that Einstein has a great distance to his theories. And he said sometimes also that when my theory arrives to mathematical singularities, the story does no longer describe the reality.
But the constant G survives, isn't it?
Yeah.
The constant G, the G is still there.
No, but the G is also varying. If you
Maybe, we don't know.
no,
We don't understand the whole problem.
no. If you look at the historical values of G, Rupert Sheldrake explains this beautifully. You know how this varying throughout time. You know they always have different values for it.
It's very difficult to measure,
Yeah.
so we can't really
Well,
be sure
it's
of
10
that.
to the fourth decimal, I think it's.
That's another question.
In your opinion, Ludwik, is it the Dirac-Eddington numerology relevant? Dirac numerology. Eddington
Dirac,
numerology.
yes, Dirac introduced also some units, great units, so now many physicists think that several numbers are important in the whole universe, but to which extent, that's the problem.
Other questions? Let's smack it.